Let's do a quick example so that we can see the dot product in action. First, let's define a coordinate system. Here we have the unit vector nx pointing to the right and ny pointing up, which by the right-hand rule means that nz comes out of the page. Now let's define two arbitrary vectors for our example. So here we have v as 7nx plus 5ny plus 4nz, and we have w equals 2nx plus 3ny plus 2nz. So to compute quantities such as the magnitude of v, or a unit vector in the direction of v, or the angle between vector v and vector w, we're going to make use of the dot product. So let's go ahead and compute v dot v. We write out the entire vector v dotted with itself, and then we expand all these terms. So we'll use the distributive law to dot 7nx with each of these terms, which gives us this line, and then we add the dot product of 5ny with each of these terms. And finally we dot 4nz with each of these terms. And now we can use the commutative law to clean this up a little bit. So for example, 7nx dot 7nx can become 49nx dot nx, and so on for the rest of the terms. So the result looks like this. And now we can simplify the dot products of individual unit vectors with each other by applying the definition. In all cases, each of these unit vectors has magnitude 1. So let's look at the angles. The angle between nx and nx is 0, so this simplifies to 1. And the angle between nx and ny is 90 degrees, so this simplifies to 0. And in the same way, the angle between nx and nz is 90 degrees, so this also simplifies to 0. So we continue this for the rest of them. So we get the result that you probably expected, which is the sum of the square of each of the components of nx, ny, and nz, which is equal to 90. Now I'm going to stop here for a moment, because you're probably wondering, why did I go through all this trouble when the rule you probably learned in high school is you could just square each component and add them all together? Well, in this case, that's true, because v is defined in terms of an orthogonal basis, nx, ny, and nz. But in general, v might be defined in terms of unit vectors that aren't part of the same orthogonal basis. And so these relationships of either 1 or 0 might not hold. So here I've written a note to remind you that the rule that you probably learned in high school to simply square each component and sum them up is actually a very special case, and it only applies when we have a vector defined in terms of orthogonal unit vectors. Again, later in this class, we're going to see time after time an example where you cannot use this rule to compute the dot product. Instead, you'll need to expand out all the components and then ask yourself what the actual dot products are. We like to think of ourselves as practical people, though, so to continue this example, let's just use what we computed before and use the simple special case rule for w. So we'll just square each of these components and add them all together. So now we can answer the first question here, which is what is the magnitude of these vectors? And if we look back at what we discussed earlier, this is simply the square root of v dot v, which is 90 here, so we have the square root of 90, which is roughly equal to 9.49, and then the magnitude of w is equal to the square root of 17, or about 4.12. So here we computed the magnitude of each of these vectors using the dot product. The next question was, how do we compute a unit vector that's in the direction of v? And that's actually pretty easy to do given what we've just computed. All we have to do is take v and divide it by its magnitude. So that looks like this, and the approximate result looks like this. It may be worth noting that for a unit vector, each component will always be less than 1 because the magnitude of the entire vector must be exactly 1. And the last question that we might want to answer is, what is the angle between vector v and vector w? So if we look down here at the definition, to solve for the angle, we need to have the dot product computation and the magnitudes of each vector. We already have the magnitudes right here, so we'll come down here and compute the missing piece, which is v dot w, which looks like this. And in general, we should expand these all out and check what the individual dot products are. But since we already discussed this is a special case where all the unit vectors are orthogonal to each other, we can just use the simple rule. So we get v dot w is equal to 37. And now we can say that the angle between v and w is the arc cosine of their dot product, which is 37, divided by their magnitudes, which are square root of 90, and the square root of 17. And if you punch this out on a calculator, you'll get approximately 0.33, which is in radians, or about 18.9 degrees. So in this example, we used two arbitrary 3D vectors that are expressed in the same orthogonal unit basis to compute some quantities that are often of interest, such as the magnitude of the vectors, or unit vectors that point in the same direction, or the angle between the vectors. And we're going to find that this sort of process is very common in the dynamics problems that we're going to solve.